So regularization is really a key tool, maybe one of the most important techniques for modern machine learning. And so this lecture will be about the basic idea of regularization. And then we will see that regularization has a lot of connections to other techniques that are not that obvious in the beginning. For example, regularization is in some sense doing a model selection, but in a continuous way. Today we did a hard model selection. We choose between model 1 and model 2 in the spreadsheet. So we had two models and we choose between one of them. And in regularization, we construct a whole continuous ensemble of different models, of different hypothesis spaces, which are parameterized by some continuous parameter, regularization parameter. Then it turns out that regularization does something very similar to data augmentation. I will tell you what data augmentation is. And I will also show you how regularization can be used for multitask learning, transfer learning, and semi-supervised learning. Okay, so to remind you again, machine learning in this course mainly means to solve an optimization problem. So we want to find a hypothesis H out of a hypothesis space or model. For example, as model, we could use the set or the space of all linear hypothesis maps. And we want to find that particular hypothesis map that has minimum average loss or training error on a training set. So the data points that we use here in this training problem is called the training set. And it turns out that the behavior of machine learning methods, which are based on this solving these optimization problems. So machine learning algorithms are, in some sense, a special class or a subclass of optimization algorithms. And the performance or the resulting accuracy of the hypothesis that we get from such an optimization algorithm or training algorithm, like the solver in Excel. The solver in Excel was one particular algorithm to solve such an optimization problem. And the result that we get is a certain hypothesis, and it might be good or bad. So it might overfit or not. And the tendency to overfit or not often depends only on a few parameters. So there's a parameter, a size parameter for the training set, M, which is the number of data points that we have in our training set. Another important parameter is the number of features we use to characterize each data point, N. And here, for example, I have shown a data set where the number of features is larger than the number of data points. This is sometimes called the high dimensional regime, or the regime of high dimensional statistics. And this is not something rare, but it's rather it's rather common that we have way more features than data points, because we can simply measure so much about a data point. Think about a data point being a person. And as features, we use all the bits that are generated by the social media posts of this person. These social media posts might add up to gigabytes a week or a year. So we have billions, trillions of bits of features for each individual. So we typically have too many raw features, and we need to find the good one or the most relevant one. So then we also have a quantity that is measuring the size of a hypothesis space or a model. I call this the effective dimension of a hypothesis space. It's a measure for the size of a hypothesis space. And what is important, what determines, or what is an indicator if a method will overfit or not, is the ratio of the effective dimension of the hypothesis space to the number of data points. And we will see, or I have derived in the textbook, that, for example, the effective dimension of linear regression. So in linear regression, we use as a model the set of linear maps. The effective dimension is exactly the number of features. So for linear regression, D equals N, the number of features. And as soon as the number of features becomes larger equal to than the number of data points in the training set, you will overfit with probability 1. So if I give you an arbitrary set of 10 data points, and each data point is characterized by 10 features, you will find with probability 1, you will find a linear hypothesis that perfectly fits the training set. But it will overfit. It will not learn any good hypothesis. It will just learn a hypothesis that memorizes the training set. There's one question. If I have like 3 features, how many data points should I choose? So the number of features is equal to the effective dimension for linear regression. For other hypothesis spaces, it's different. So I cannot tell you the number of data points you use or you need to use for data points with 3 features depends on the model or hypothesis space that you are using. If you use the hypothesis space of linear maps, then you need more than 3 data points. Yes, so just what is important here, the validation error will typically increase as soon as you go beyond the critical value of this ratio, effective dimension divided by the sample size equal to 1. So this is a critical value. Above this value, you will see that the training error will become 0. So you will be able to perfectly fit the training set. However, the predictor or the hypothesis that you learned is doing no good at data points outside the training set, which means the validation error goes up. And there is some minimum here. There's some optimum, some sweet spot for the validation error. And we need to tune the model size or the effective dimension to exactly hit this sweet spot, to minimize the validation error. And regularization techniques allow to tune this effective model dimension. So regularization techniques allow to move along this axis here and find the sweet spot with the minimum validation error. So as I said, the important quantity is this ratio of effective dimension divided by the number of data points in the training set. We need to get this ratio below the critical value 1. And there are, of course, 2 options here, obviously. Either we increase the number of data points in the training set by using more data for the training. So we make M larger, or we do not increase the data, but we try to decrease the effective dimension. We make the model smaller. Do you remember how I did this in the Excel spreadsheet? How did I try to bring this dimension down of the model? Does any one of you remember? Let me show this again. Yes, I removed some features. So let me show this again here in Excel. When I started to first train model 1, I trained all the weights, but then this validation error was much larger than the training error. So let's look at it again. It's for free. Using the solver is for free, so let's use it. So now I solve this optimization problem, the training problem, I solve. Training error goes down because I use a larger model. But at the same time, the validation error goes down, goes up 3.6. So, and then remember, we said, okay, this seems to be overfitting. So let's reduce the model dimension, the effective dimension. And how I did this? So I wanted to bring D down, the effective dimension. I set some of the weights to 0 and optimize over a smaller set of features. So this means I use a smaller hypothesis space with a smaller effective dimension. That was exactly what I did. Let's use the first 5 one and solve. So the training error goes up. a bit. So the validation error didn't go up that much, so I reduced it too much. I think I used also the 6. Wait, I pruned it too much. I made this D too small. So let's now look again. Yeah. Now it's reducing the validation error a bit. Not too much. Yeah, but a bit. So what I did now in Excel was I navigated this curve. Let me show you again here. What I did now in Excel was I navigated this curve. So first I reduced the model dimension too much. So I increased the training set, but also the validation error. Then I kind of I reduced it a bit, the model dimension. So I increased the training error, but I also reduced a bit the validation error. So I moved along this curve here downwards. So what I did in Excel was a hard model selection. So I choose the D between discrete values, 5, 6, 7, because the effective dimension of linear maps is the number of features. And in regression, we will do this more smoothly. But let's look first at the other option that I didn't explore in Excel, which is to increase the number of data points. And how could we increase the number of data points in this Excel example? So using weather data, where can we get more data? Where could we get more data? Yes, from the same place where I took the original data, from the FMI. However, in some applications, this is not an option. We cannot get easily data. And in this case, we use data augmentation techniques, which is really a cute trick to get more data. And the idea is to create synthetic data points, to say, well, the relation between the features of a data point and the label should be not so much dependent on the precise values of the features, because there's typically anyway always some noise in the measurements used for getting the feature values. So I could say equally well to the original data points, I could also have measured a slight perturbation of the original data points. So I add a bit of noise. And these are called augmented data points. And you see all of a sudden, instead of the original raw data points, the blue ones, which are 3, I now have 3 times 3 data points, 9 data points. So I have increased my original data set by a factor of 3. And why should I stop at 3? Let's do 100 small perturbations for each data point. So I multiply then the number of data points by 100. Another example, instead of adding noise, I can use some intrinsic symmetries. For example, if you want to develop or want to learn a hypothesis that outputs cat if an image shows a cat, or no cat if the image doesn't show a cat, then this hypothesis should deliver the same results if you show it some cat image or some rotated cat image, because a rotated cat image is still a cat image. So you can add these 3 further data points to your training set, because you know the label. The label didn't change by rotating them. So if you know that this was a label cat, then you know the label of these data points. Another example, flipped images. So if you flip a cat image, it's still a cat image. Shifting, if you shift it around a bit, it's still a cat image. So you see, we can use some symmetries or transformations that doesn't touch or doesn't change the content of an image or the label value to create more data points. So this is called data augmentation. And this is very convenient in Python, for example. This is one line of Python code to multiply your data set by 3, just by applying 3 different shifts of the images. Okay, now the second approach. So first approach was to increase the data points. Second approach, make the model smaller. Decrease the effective dimension by using a smaller hypothesis space. And So what does this mean? What I did in Excel, when I reduced the number of features, I did the following. Instead of solving the original learning problem, so finding the best weights for all the 9 features, I just looked at all the weights using the first 6 features. So this is a subset. I replaced the original learning problem with another learning problem on a smaller, or I call it pruning, make it smaller. I made the hypothesis space smaller. And in this way, the smaller hypothesis space has a smaller effective dimension, and therefore the hope is to move here to the left. So if I'm here, if the hypothesis space is too large, I try to move a bit to the left by making the hypothesis space smaller. And it turns out that you can do this by a technique called regularization. So regularization is done by adding to the training error. So this is the average loss on a training set, or the training error that we always looked at so far. So we tried to minimize this. We add another component to this training error, which measures the increase or our expectation or anticipation of the increase in the loss on new data points outside the training set. So this is the error on the training set. And this term here measures our, or is our guess for how much the error on new data points will be larger than the training error. And you can come up with such guesses. It sounds a bit hard to believe at the moment, but there are ways to come up with such guesses, good ways and reasonable ways. However, it turns out that we can understand these regularization terms from a different perspective. So we can find an equivalence. So this is related to optimization theory, and you don't need to understand the details behind it. This is a topic of optimization courses, master level courses. But I just want to explain here that this adding this regularization term, when you then minimize this objective function, is equivalent to minimizing only this part here, minimizing the training error, but on a smaller hypothesis space. This relation or this equivalence is also known as duality in optimization theory. So these two problems are dual in a specific sense. In particular, the solutions of this problem are the same as the solutions, or in this case, the solutions are the optimal hypothesis for this problem. And the reduced hypothesis space here is directly related to the regularization term. So the larger this lambda here is a parameter, the larger you make this regularization parameter, the smaller this pruned model becomes in this equivalent learning problem. So what regularization does is it reduces the effective hypothesis space, and it makes the dimension, the effective dimension of this hypothesis space smaller if we make this lambda larger. So regularization is in a sense a soft or a continuous model selection. For larger regularization parameter lambda, the smaller this effective hypothesis space in this equivalent learning problem becomes. And in the extreme case, if we make lambda extremely large, this means that the effective hypothesis space reduces to 1 point. So the training error then becomes meaningless. The only thing that matters is to make this regularization term as small as possible. Okay, so I will stop now here. I will then continue on this lecture on Wednesday. But I just wanted to give you a first glimpse about the basic idea of data augmentation and regularization. We will then see in the Wednesday lecture that data augmentation and regularization is equivalent in a certain sense. In particular, this regularization term here can be interpreted as the additional training error that one would get if one replaces each original data point by a whole random, by an ensemble of random variables, which are random perturbations of the original data point. And if we compute this additional or extra training error on this augmented or perturbed data points, what you get is exactly this regularization term. So it turns out that regularization is equivalent to data augmentation. Okay, so as a preparation for this Wednesday lecture, I highly recommend to read through chapter 7.3 of my book and maybe have already a look at the slides. You can find those slides on the My Courses page under section Lectures. Okay, that's all from my side. Have a nice sunny rest of Monday and see you again on Wednesday. Bye.